Cool. All right, we'll finish up. Shouldn't take too long. So what I wanted to do, just to disillusion you of thinking that it's as simple as one neuron, one neurotransmitter, one thing, I just wanted to give you an idea of just how complicated this neurotransmitter business is. So if we take a look at just serotonin, 5-hydroxytryptamine, there are, as I stated earlier, 7 different receptor subtypes for serotonin. The 5-HT1, the 5-HT2, 5-HT3, 4, 5, 6, and 7. And then some of these receptors have receptor subtypes, such as the 5-HT2 has the A and B. So you have the 5-HT2A and the 5-HT2B. The 5-HT5 has a 5-HT5A and a 5-HT5B. And serotonin attaches to all of these. Some of these are G protein coupled, and some of these are ligand-gated ion channels, or ionotropic. How crazy, no? It's just a mess. So what I want to do is, because it's interesting how many medical treatments and therapies and problems are just come out of just looking at serotonin and its different receptors. So if we look at the 5-HT1 receptors, we've actually created a class of drugs that inhibit or block those receptors. And some examples of those are drugs like Geodone and Buspar. And these are psychiatric drugs, right? Antipsychotics. So somehow blocking these receptors is associated with reducing the psychotic signs and symptoms of people like with schizophrenia and schizoaffective disorder and things like that. Now if we move over to the 5-HT2, there are 3 subtypes, A, B, and C. Okay. We know that the 5-HT2A receptors are associated with psychosis when they're activated. Okay, and this is where a lot of our hallucinogenic drugs, okay, particularly a class of hallucinogens known as the indole alkylamines. And these include things like DMT, things like psilocybin, bufotenin, are very, very good at activating the 5-HT2A receptors. And in fact, we've actually given drugs that block the 5-HT2A receptors and have prevented much of the hallucinatory effects of these hallucinogens by blocking these receptors. Now the 5-HT2B receptors, one of the areas where they're important is in stomach contraction. The 5-HT2C receptors seem to be important when it comes to the production of cerebral spinal fluid. Like, wow, the serotonin is just important everywhere. And this is just one of many, many different types of neurotransmitters. The 5-HT3 receptor is actually an ion channel, unlike the 1 and 2, which are G proteins. And this one is actually very important in the vomiting centers of your brain. And there is a very common drug that we give that actually blocks the 5-HT3 receptor, and that drug is known as Zofran. Any of you ever received that in the IV? It's a very common drug given in the emergency room, given by paramedics, given in the hospital if you're admitted, that helps prevent vomiting, and it blocks the 5-HT3 receptors. The 5-HT4 receptors are G protein coupled, so they're metabotropic, and these are associated with gastrointestinal distress. And there's a drug that blocks these receptors that we can give to help with GI upset, and that is a drug called Reglan. And then the 5-HT5, A and B, the 6 and 7, who knows? We don't know. We're really not sure what goes on there. Right? So that's just one. Okay, that's just one example of all the different receptors that we have just for 5-HT. When we go back to acetylcholine, a word that I want you to put in your memory is cholinergic. Cholinergic. Cholinergic receptors are receptors that are activated by acetylcholine. Okay, so any receptor that gets activated by acetylcholine is a cholinergic receptor. You guys okay with that?
You said they were activated
by acetylcholine. Yeah, so cholinergic. And there are two major types of cholinergic receptors. These are known as the nicotinic, and the muscarinic. The nicotinic receptors tend to be located in muscles. For example, skeletal muscle. Right? The receptors for acetylcholine in your skeletal muscles are nicotinic cholinergic receptors. Muscarinic receptors tend to be found in like certain types of smooth muscle organs and glands. This will come back to haunt us here in a couple weeks when we actually do our lecture on the peripheral nervous system. We'll do a whole lecture on just the peripheral nervous system and a whole lecture on the central nervous system next week. All right. And then finally what I want to do is I want to end on a more complicated note, even more complicated. And that is to talk about a class of molecules known as the neuromodulators. These are similar to the neurotransmitters, and what they do is they modulate or they alter neuronal activity, but they do it in some rather convoluted and complicated ways. Okay? Their effects tend to be long-term, and their action tends to be delayed. Okay, so unlike neurotransmitters, which tend to either inhibit or excite rather quickly upon release, right? They don't really play around. They attach to the receptor, they do their thing, they go home. That's that, right? You either have an excitatory or inhibitory graded potential produced. That's not necessarily the case with these, okay? These neuromodulators involve multiple steps, multiple pathways, and they may either be pre or post-synaptic. Okay, so they may alter how a receptor responds to a neurotransmitter. Maybe they'll make the receptor respond more vigorously or less vigorously. Maybe they'll activate enzymes that help produce more receptors, or they'll inhibit enzymes and they'll produce less receptors, or they'll produce another kind of receptor. Like do lots of different things. A specific class of neuromodulators are what are known as neuropeptides. Okay, so these are amino acids that, right, you bind multiple amino acids together to produce peptides. Okay, and neuropeptides specifically are receptors that activate enzymes. So they bind, these peptides bind to the receptor, and then the receptor goes on to activate enzymes, and then these enzymes go on to catalyze chemical reactions. And this can be either presynaptic or postsynaptic as well. An example of a neuropeptide or classes of neuropeptides that I want to throw out there are what we call the opioids. Specifically the endogenous opioids. And whenever I use the term endogenous, what I mean by endogenous is produced within the body. Okay? So when we say something is endogenous, we mean that it comes from within the body, right? Because some substances might come from outside of the body, right? A certain drug, like dopamine, can be given exogenously or outside. We can inject it into somebody. But if dopamine's produced within your brain, then we would say that that is endogenous. So you do have endogenous opioids, and these opioids have their own receptors, and there are 3 general receptor types for the opioids, and these are the mu, the kappa, and the delta receptors. And specifically, it is the mu receptors that can cause problems when it comes to people that overdose on opioids, because these mu receptors can suppress the respiratory drive. Make our patients might quit breathing. But when we talk about endogenous opioids, there are several classes. You guys have ever heard of the term endorphin? Heard of that? Oh, my endorphin levels are really high. Well, endorphins are actually endogenous opioids, as well as enkephalins, dynorphins, and endomorphins. Okay, and these are all released during times of high stress, okay, or injury, sometimes illness. And what these can do is these can attenuate the pain. Okay? These can block some of the pain response. They can modulate neurons, and these neurons will be less able to fire, okay, and less able to send, okay, sensory or afferent information up to the brain and tell the brain that there's pain. And that might be a good thing if I need to run away from a lion, right? If a lion's chasing me and I need to run away from that lion, okay, do I need to worry about my knee hurting or my muscles being sore? No. And so that pain gets blunted by these endogenous opioids, the endorphins, the enkephalins, the dynorphins, and the endomorphins being released. And then eventually they go away, right? And then you get really sore and you don't feel very good afterwards. All right, guess what? I made it through nervous tissue. Sorry, it's a rough one, but there you go. I'll see you guys in the lab. Please wear the appropriate attire, shoes. Don't bring anything to drink or anything like that into the lab. Just because we'll be working with a lot of tissue. And I'll see you guys there. I'll try to get these videos up as soon as I can.